All right, so good morning. Hello. So let's get started. Do you have any questions? Okay, so where did we leave off last time? Okay, so last time we were discussing 10.8, the maximum likelihood. Estimators or MLEs. Okay, and so the point of MLEs is that first we view the likelihood function, right? So we have x1, xn, IID, right, sample. The function L of the sample value x and the parameters theta, right, is a likelihood function. Which, right, is basically the joint PDF or, joint probability function. Okay. And from our point of view, what we want to look at this function as fixed in x. Okay, the sample values is fixed and theta are left unknown for estimations. Okay. X is fixed, right? Known. So it is random, right? If we do another sample, or if when we want to investigate the property of the estimators. For now, we want to find the estimator. So we just keep theta fixed, okay? Sorry, we just keep x fixed, okay? Theta, right, is unknown. Theta, the vector theta, right, the population parameters are unknown. And it is the variable, right? It's not random, okay? It's a constant, but it's a variable that we will maximize over. Variable to be maximized over. Okay. So the point of view is that the MLE theta hat MLE, right? And this could be a vector too, in the sense that there are more than one parameters that we will maximize over, will be the maximizer of the likelihood function in terms of theta. Okay. And we made one observation that the maximizer of the function and this log is the same, because the log function is increasing. So we will maximize, right, the log likelihood function and then find the MLE estimators that way. So the usual approach, okay, the usual approach is to differentiate, right, the log likelihood, okay, in terms of theta, and find critical values. Okay. Now, let me say this, right? Caution or pitfall. So two common mistakes, or actually one common mistake, right, that students tend to make is critical values does not mean are not only the point where the partial is equal to 0, okay? In other words, setting the derivative equal to 0 is not the only point where you have critical values, okay? As you'll see. The second one that does not is really a caution, but more like a remark, is that critical values are not enough to you know, make sure, or to say, to make sure that the value, right, or are not enough to make sure that they are the max. Okay, so in other words, if you just find a point where, let's say, the derivative equal to 0, that doesn't mean that the function is maxed at that point, right? Like this example right here from calculus 1, right? The derivative equal to 0 here, like suppose you have theta here, and then, you know, this is L of theta. Then even though the derivative is equal to 0 here, it doesn't mean, yeah, I mean, like, okay, we spoke about this last time, right? You should, if you are a very good person, well, I never claimed that I'm a very good person, so I won't. Or actually, the point is this, that most routine questions, right, tend to land you on the max, okay? I have never seen people really having to analyze the second derivatives, okay? You ask me why? You don't want to. You should use log. But I mean, here I write L because, you know, the maximizer is the same, whether it's log or ln. But in terms of practicality, in terms of calculation, you do not want to use log. You can. It's just going to be super painful, and you're going to get lost. Why? Yeah, I mean, you have seen many examples, right? We'll repeat it for you, but we'll repeat it for you. But let me go back to, Madhav's question. You do not, sorry, we do not use a second derivative test, all right, in the usual context of examples that we do. I really don't have like a very good explanations of that. It's just, you look at it, it seems fine, right? You basically we're lazy. So on the exam, I would not, you know, like require you to do second derivative tests. I'm saying this, you know, out of conscience because, right, I mean, I cannot state something not rigorously, and there may be examples out there that does not, right? That may trick you on this part. Okay, so I want you to be aware. But most routine questions that we do fall into this line. Like we do not do the second derivative test. It seems okay, but yeah, I claim that, of course, that statement is not rigorous in of itself. So just keep in the back of your mind in case you see something strange coming up. Okay. So well, example, right away. And I think the easiest one is like the exponential. Where, right, the likelihood function in terms of lambda will be 1 over lambda to the n e to a minus sum over xi over lambda. Okay. And so here, Jian Lang's question, right? Well, do we want to work with this function and differentiate with respect to lambda? You can, right? There's nothing wrong with that, but absolutely differentiating this function with respect to lambda is not pleasant because of the product rule, right? And why do we have to do so if we have some easier way to deal with? In other words, if we take the log then I hope you're convinced that this function is much easier to differentiate in terms of lambda, just out of practicality. Okay, and the practicality is very easy to understand because the likelihood function being the joint distribution of independent variables are always product, right? Unless you deal with non-independent functions, I don't know. But when we deal with independent random variables, which is always our context, right, IID, the product structure, right, makes it very nice to work with the log, because the log just turns the product into the sum, and differentiating with the sum is always easy. So that's the point, right? And then if you differentiate, you got minus n over lambda plus sum over lambda square set equal to 0. You got lambda equals to x bar, right? And then here's where I guess, Madhav, I was saying that the moment I see lambda hat equals to x bar, I don't think I doubt it too much, right? I don't think I doubt it too much because, yeah, that looks okay. That looks right, right? But if you are conscientious, then you want to differentiate this one more time and make sure that the second derivative, right, at this point is negative, for example, to make sure it's max. But because it is statistically speaking, this is what I expect. I don't know. I skip here, right? And again, right, I don't hold you to it on the exam either to have to do the second derivative test, as long as the answer is correct, right? Whatever that means. Question here. No, yeah, no, it's not too complicated. We're just being super lazy, I admit. Yeah, and I think there is a generic result that shows that most likelihood function you look at, the second derivative are always negative. Okay, but that requires us to look at the more abstract case, abstract structure, deal with some math. But yeah, there is an abstract result like that too. I'm not sure about the precise statement, but as far as I'm aware, the second derivative somehow always negative. It's concave down, simply because of the density structure. So yeah, you have that working for you too. All right. Well, good. So that's kind of reviewing what we did last time, right? So let's catch up with where we left off, which is the normal, right? The normal example. Okay, so we start with the likelihood function, but notice the likelihood function here is a function of two parameters, and it's going to be 1 over 2 pi sigma square raised to n over 2 eta minus sum xi minus mu square over sigma square. A word of caution, all right? I am so used to this that I just write down. For you, right, when you're new to this business, I think even remembering density, right, may be a little bit challenging, right? You have to kind of recall what it is. So don't force yourself to write down the final answer like I do, okay? It might be too much of a jump. It may involve mistakes. What you should do is you should start with product, right? And then individual density at individual point, and then write down the product, etc. Right? Break this down into several steps so you don't make mistakes. Okay? I mean, nothing wrong with going like this, right? I mean, my philosophy is if you got a correct answer, I have nothing against you. But of course, if you make an error somewhere here, then all the answers you say down the road will be wrong. Anyway, right? So this is the joint density. We want to find mu and sigma, right? Mu hat and sigma hat square. So we will differentiate. Oh, sorry, we take the log first, right? Take the log, which is minus n over 2 log sigma square minus sum over sigma square, like that. Okay, and so what we said here last time, right, is to differentiate with respect to mu and differentiate with respect to sigma square, okay, and set equal to 0. So the point to see here is, I think in terms of calculus, we're very used to seeing sigma as the variable, right, rather than sigma squared. Here, right, I hope you see that differentiate with respect to sigma square will be slightly different, right, in terms of like the final answer. So what I'm saying is like, you know, sigma square hat is not equal to sigma hat square if you follow strictly what you mean here, right? So sigma hat square means you solve for this when you differentiate with respect to sigma, right? Sigma square hat means you follow this when you differentiate with sigma square. So what we do here is, right, technically speaking, sigma square hat. But, you know, like this notation, people tend to kind of, you know, bundle them together so they don't differentiate. But okay, so we're looking for the maximized variance. We're not looking for the maximized standard deviation, okay? So differentiate here, we get, oh, and there's a constant terms here, right, that we don't care. The constant term comes from the 2 pi. And then, so that will be differential respect to mu gives us 2, right? Sum of xi minus mu divided by sigma square, and we set that equal to 0. Okay. Differentiate with respect to sigma square gives us minus n over 2 sigma square plus sum xi minus mu square divided by sigma to a fourth. Set that equal to 0. All right. Any question here? So notice, right, this is just an equation in mu because sigma square is canceled, right? And so here you got exactly mu hat is x bar. Okay. So we plug that into here, right? And get, let's see here. Hold on. I feel like I'm getting extra 2 here for some reason. I should not get a 2 here. Just give me a moment. So if I plug in here, right, I mean, what seems to happen, I know that the answer should be sigma hat square or sigma square hat, whatever, is going to be sum of xi minus x bar square divided by n, right, which is really just s prime square. But somehow I get an extra 2 here, so that's not right. There's no lambda here, or what are you saying? Right, we'll look at from this density. Yeah, but because it's going to be square root of 2 pi sigma square, right? And then I raise it to the n power, so I get n over 2. When I take the log, right? When I take the log, I get the n over 2 in front. So I don't see why the 2 cancel. Did I make a mistake somewhere where the 2 cancel? Then it must be. I don't have a 2 here. I should not have a 2. That's weird. Oh, you know what? I wrote down the wrong density. Okay, so I advertised that you should not make a mistake like this. I did. The density of the normal has a 2, right? There's a 2 here. There's a 2 here. Always good. Apologize. Yeah, you see, like making a mistake upstairs has consequences. I myself make mistake. There's a 2 here, okay, from the normal density. I apologize. Are we okay? So yeah, always good. Any question? So, right, the only message here is that, or the only thing that's worth noticing here is that the derivative is with respect to sigma square rather than sigma, okay? All good? Math makes sense? Okay, cool, very good. So yeah, I mean, like, I don't know. I mean, not advertising for myself, but reality check, right? Knowing what you should expect also helps. I mean, I know there's no way it should be S prime some there's a two here. Things should work out okay, right? Things should work out in a reasonable estimators. So I knew that I made a mistake upstairs somewhere. But anyway, right? Having awareness of what you're doing should also help. Okay, not excuse for myself. I did make a mistake. All right, so let's move on to the next case, which is the uniform. Okay, so here the unknown parameters are A and B, okay, alpha and beta. So let's take a look. What do we want? What do we want? So what the MLE, oh sorry, the likelihood function, right, of X and A and B is 1 over B minus A to the n, right? Because each individual density, right, is 1 over B minus A, right? And so when you take the log, that's going to be n, right, log of B minus A. You differentiate with respect to B. Let's say you got n over B minus A set equal to 0. You differentiate with respect to A, you got minus n over B minus A, you set equal to 0. Okay. Well, let's see here. B, right, is the right point, A is the left point. This can never be 0, right? Same thing here, this can never be 0. What's going on? This is a deliberate mistake, by the way, okay? I know what I'm doing here. There's no, this is a mistake. But what is wrong here? What is going on here that is wrong? First of all, do you notice anything strange that definitely is wrong? You don't even have to go down here. What is wrong in this formulation? Notice anything missing? No X, right? Yes, Samuel. No X. No X is the red flag. Why? Because we're in the business of statistic. All right. If anything you do that somehow the sample disappear, then what's the point? Right? Okay, you can make a mistake anywhere, right? I mean, like a calculation mistake like this, but notice even in my calculation mistake, the sample still stick around with me, right? But here, notice that by a miracle of my calculation, the sample disappears. That is a sign that whatever I do is nonsense, right? Pay attention to being nonsense versus being making a mistake, right? Arithmetic mistake is fine. I make arithmetic mistake too. Nonsense is a little bit harder, right? And then don't take offense with that. Nonsense just means that what you're doing just doesn't mean anything, right? And then we should appreciate that, because with no sample here, what are we doing? There's no statistic, right? So where is the sample? Where is a sample? Anyone know? So the sample, right? The sample is hidden from the density. In other words, actually, this density is not precise to begin with. Okay. I know that a lot of students, right, like to write the density down like this. But when you think about it, this is not the right density. Okay. When you write something like this, what you mean is the density is always like this for any x, which is not the case at all, right? The density is this only for x between a and b. Okay. So this is also like the density, the joint density like this for x between a and b. You can include equal, even though that's event of probability 0. Okay, so that's like that. But of course, you know, when you write something like this, is kind of awkward, because the point is you want to view the likelihood function as a function of a and b. Okay, you want to view the likelihood function as a function of a and b. So this is fine, right? Or in other words, the point of the uniform distribution in terms of parameters is the parameters, you know, kind of serve as a boundary, right, of the support. So the sample only shows up, right? The sample does not show up in terms of the value of the density itself, right? Because it's uniform. So of course, it doesn't matter where you are, the value of the density is the same, right? The sample only shows up with respect to the support, right? With respect to the A and B. So how to incorporate that into here as a function? Because again, right, the point is you want to now flip things around. You want to look at the likelihood function as a function of A and B. So to do that, okay, you introduce this idea of the indicator function. Okay. So the indicator function is a stylized one. And here I'll just do the indicator function of a less than x less than b. Okay. Well, what is it? What it is just basically, you know, you can view it as a Heaviside function. I think Heaviside as in I think little I maybe. I mean, just a name that's just fancy, but basically, right, a and b here as a function of x is 1 between a and b, and 0 otherwise. Okay, so maybe let me try another color. 1 here and 0 here, right? That's the indicator function. All right. Now, of course, the indicator function can be turned around to view as a function of a or b. So in other words, as a function of a or b, right? What you're seeing is, so as a function of x, this is as a function of x. As a function of a or b, let's say as a function of a, what does this indicator function do? Right? Let's do equal here. What this indicator function does is that it's going to be 1 up to x and then 0, okay? And then 0 otherwise. Like that. Okay, as a function of a. So if you want the abstract definition, an indicator function of anything is going to be 1 if E is true, and 0 if E is false. Okay, so it's just supposed to signal that this holds. But if you view it from the point of view of X, then this holds when X stays between A and B. If you view it from the point of view of A, then it holds if A is below X, right? Like that. Is that okay? Is it clear about the indicator function? All right, so then the density of a uniform, okay, X is a uniform AB. The density of a uniform will be written like this. And that would incorporate all information on A, B, and X. Because, right, it says that this is going to be 1 over B minus A if X is between this range, because this indicator function is 1, and then 0 outside this range, which is also true, right? So this indicator function just serves as a convenient way to incorporate that boundary into the density function. Okay. Now, so if you look at the joint, right? If you look at the joint, so by the way, right? So all these are wrong, okay? Let me just do this back. If I erase this, right? This is what I was writing before. This is wrong because no X, right, is present. Okay. So now to write the likelihood function in terms of X, A, and B, what we'll have, right, is going to be a product, right, of individual ones. So the product of this guy is easy, right? It's going to be just 1 over B minus A to the n, which is exactly what the term we expect. But we still have a product over the I. Like this. All right. Is this product that we need to work on? Is this product that we need to work on? Okay. But this way, right, we incorporate the dependence of the sample, right, on the parameters into the likelihood function. Compared to here, right, exactly that's missing. This part is missing, and that's why, right, the analysis above is wrong. Any question? So a bit of abstract, okay? So let's take this point of view. Suppose we have E and F, two events. We have indicator function of E, we have indication of F, right? Why did we not use, maybe that's what you're asking, right? Why did we not use the derivative of log? Or you mean here, the log? You mean, are you asking about this? Or are you asking about the new one that I'm discussing right now? I know the normal, but like the normal use a log. But are you asking about this one not using the log, or which one does not use a log? I did, right? Right here. Oh yeah, this one, right? Yeah. Well, I'm not there yet. I'm not there yet. I'm still discussing the dependence of the samples on the parameters. Then we'll maximize, right? So the point is this, that if you cannot get a hold of the likelihood function, if you do not understand the likelihood function very well, then forget about maximization, okay? Maximization in some sense is just a technical calculus step. I mean, I'm not saying it's easy, but I'm saying it's not statistics in the sense that it does what it does, right? Optimization is a field by itself. But if you input a wrong object, okay, if you input the wrong likelihood function, of course the optimizer, right, being a machine, whatever it is, will spit out nonsense. That's actually the message. So what I'm trying to say now is, what is the right object to feed into the optimizer, right? And then we'll discuss how to optimize it. But if you feed the wrong object in, forget, right, about the optimization process. It's not gonna make any sense. Is that okay? So I'm still discussing the likelihood function structure of the uniform. Okay, so the point being, right, is that when you look at the joint, you will pick up a product of indicator function. Again, right, the indicator function comes from the boundary, okay? The indicator function comes from the boundary of the finite support of the uniform. All right, so to understand the product of indicator function, right, let's just look at an easy example. If we have, right, event E and event F, and if we take the product of these two guys, what are we looking at? Is there any way to look at this product of the indicator as something nice? Yeah, very good, but indicator function of what? That is true, right? Because 1 times 1 is 1, 1 times 0 is 0. So it can only take 1 and 0. So it looks like an indicator function. But indicator function of what? Well, when is this product 1? Exactly. It's 1 when both of them are true, and it's 0 if one of them is false. So that's exactly the logical end, right? Or intersection, right? So if you want, this is exactly indicator function of E and F. Okay, that's it. That's very easy. So multiplying indicator function means you take the intersection of the event. So from here, right, I hope that it's very clear that the likelihood function that we're looking at is going to be just 1 over b minus a to the n, indicator function of a less than or equal to x1 less than xn less than b, where x1 and xn are our sample, our order statistics. Okay, see how the order statistics come back naturally, right? That's where they are. They are there to interact with the parameters in terms of the boundary points. Any question? All right, so right, so now we have got the support of the log function, of the likelihood function correctly. We could take the log if we want, right? We could take the log if we want. So let's see, right? The log is again, right, n log of b minus a, right, plus log of this. Okay. So let's see if you differentiate with respect to b, right, and set equal to 0, then you get this. But this being 1 or 0, right? So differentiate, it gets to 0. So I'm back to what I got before, isn't it? Right? This function being 1 or 0, so differentiated gives me 1 or 0. So I'm back to square 1 again, like where I was before, like this. What's the difference? So the optimization doesn't work either. Any idea? You understand what I'm saying, right? This differentiate to this in terms of b. But this function, right, the indicator function being 1 or 0, right? You differentiate once, you get 0, right? You differentiate 0, you get 0. So what are we doing? So the point being, right, is that you're not paying attention. You're not paying attention because you're not doing calculus right. Or I mean, I'm speaking before. Those are the words of a student, maybe a calculus student, right, saying that. A more mature mind would probably not see that. What's the point? The point is this, right? It's really not a function of. This is not really a constant function. Okay, it's not a constant function because, again, what's the point of view? The point of view is now you're looking at things from the point of view of B or A, right? B or A are now variables, right? So because we'll differentiate with respect to B, right? Let's look at from the point of view of B. What does B see? B see that, right? It must be above the max, right? So if it stays above the max, it'll be 1. If it stays below the max, it will be 0. Yes. So the question is, as a function of B, is this function differentiable? As a function of B, right? This right here, pay attention. I'm drawing, right, a function of B, right? So let's say there's a calculus 1 midterm exam asking you if this is a differentiable function of B. What would you say? What would you say? Well, the answer is, right, is differentiable. No. I'm not talking about integration. I'm talking about differentiation. Derivative, slope. Yeah, no, because right here, right, this is not differentiable at all. Exactly. So it's not differentiable where? Not differentiable exactly at x. So actually, right, remember, go back to what I said. Remember, I said the caution. Critical values are not the only points where the derivative equal to 0, right? If you go back to your, calculus knowledge, right? Once upon a time, there's exotic ones. Critical values are points where derivative equal to 0 or undefined. Look it up. It's very interesting, right? Not just what transformation are we looking at here? What are you saying? What transformation do you have in mind? LAP? I'm not sure I follow what that is. Laplace? No, we're not getting anywhere near that. We're not doing Laplace transform. I know what you're talking about. The Heaviside function Laplace transform is something. No, this is not what we're looking at. Yeah, but the Heaviside function does show up in Laplace transform. I'm aware of that. Sure. Yeah. But here we're just doing very simple, right, optimization, where you see you're optimizing in terms of B and A. I'm telling you that if you look for critical values, you will pick up xn as the critical value for B. Okay? Absolutely, right? Actually, let me say this, right? If you think about it, look at the absolute value function. If you were to find the minimum of this function using the derivative approach, will you get any point? I mean, if you were to really look for derivative equal to 0, you will not, right? Because the derivative equal to -1 or 1. Obviously, this point is a critical value, but you will not see it unless you also consider points where derivative is undefined, isn't it? So again, right, just reminding you of your calculus. All right, but because you're so used to setting things equal to 0, you kind of miss, right, the other part, which is rare, but it's there, right? And it's here, it shows. Any question? So same thing, right? Then x1 is critical value for A. Okay. And, right, this is enough to show that B hat is xn, B hat MLE, A hat MLE is x1. Okay. So the message here is no derivative equal to 0 going on here at all for the uniform distribution. If you were looking for that, you will be into a world of confusion where you don't know where you're going. Any question? So right, this approach is not good at that point. You just say the derivative, right, does not make sense for B at this. That's a critical value. Any question? All right, so this is very, very important. Pay attention to this, all right? Pay attention to this. Because if I have to say anything, right, this is the only other interesting part of MLE, right? The rest, I trust that your calculus is fine. You can differentiate, set things equal to 0, okay? But where I'll talk more about this, but get the spirit of it. But I want to say yet more, okay, about this, because I mean, technical, right? Technical approach is fine. Technical approach is fine, but I would like to have a more natural approach to things. So a let me say a less technical approach. To finding the maximizer. Okay. So the likelihood function, if you recall, is 1 over b minus a raised to the n, indicator function of a less than x1, less than xn, less than or equal to b. Right? Now, what is the goal? Right? Forget all the calculus. What's the goal? The goal actually is very simple. You can describe it to, you know, a high school student. The goal is for me to find A and B that maximize this quantity, whatever that is. Okay. That's my goal. Now, okay, just look at this, right? They say with the eye of the child, if you will, like forget all calculus. Just look at it. What do you see? What kind of A and B do you want to choose that would maximize this? No. Why 0 and 1? 0 and 1 are just kind of Random, right? Random in the real sense of a random, arbitrary. Where does that come from? So first of all, right, the only thing I know is I want to choose B as small as possible. Also, I'm very suspicious of where you get the one from. Where does the one come from? Oh, okay. So actually, I see what Madhav was saying. You get the right spirit, but your one is very weird. What you're saying, right, is you want to choose the B and A so that B minus A is minimized, right? You want to choose B as small as you can, A as large as possible, or frankly speaking, you choose B and A so that B minus A is as small as possible. Yes, that's what you're saying. Yeah, by that one. But by the way, right, that one is very strange. So you want to be careful of what you say. You have the right idea, but what you put down is suspicious, right? So, okay, everyone else, I hope you see why I do this, because you're dividing by this. So the smaller, right, you divide, the larger, right, the fraction, okay? Now, okay, so back to Madhav, right? Is it possible that I choose B minus A less than 1, like he suggested? Or can I do better than that? Or I have to do worse than that? What is as small as possible here for me? What is as small as possible here for me? You can't. You forget something, right? What you're doing, you're saying a very routine answer that anyone would say that, except that you're not being aware of context. Is B minus A free to approach 0 here? So let me show you a picture, right? No, why not, Christine? No, not that. Yes, they are constants in the sense of they are non-random. So actually, they're deterministic. Oh, not that reason, Christine, right? No, I mean, we take limit anyway, so it's not about being undefined. That's not that. So Madhav, right? Yes, they are constants and they are deterministic. That doesn't mean they're not variables in the sense that we can, again, we're maximized over them, right? They're unknown. So we choose a candidate for them. So B is high and A is low. What does that mean? All right, you all saying this without being aware of the statistic context. Exactly that. I was waiting for that, right? Why? Because let's look at the picture. A here, B here, right? That's your uniform. What happens in between? What happens in between is your x1, your xn, and everything else. That's your sample, right? That's always the case, isn't it? So now what are you doing? You're pushing B as small as possible. You're pushing A as large as possible, right? To minimize the gap. Well, tell me, how far can you push B to the left? How far can you push B to the left? Yeah, right. Reality would not allow you to push B over here, because if you push B over here, what you're talking about here, this cannot be a sample, right? Because uniform AB means it's between A and B. So you can only push B as far to the left as here. You can only push A as far to the right as here. Agree? So in terms of the maximizer, if you see this picture, automatically you see B hat is xn, A hat is x1, period. If you want to maximize it, no need for calculus. And by the way, right, this also addresses the second derivative, whatever. There's no second derivative here, right? Here, actually, I can show you clearly that this will be the max. This will be the maximizer, because that's the best I can do, right? This is as clear as possible in terms of like maximizer. Any question? Okay. So when, okay, so when in what situation, okay, in what situation does you know, this approach show up? Okay, in other words, why, when you care for the order statistics, for example, in other words, right, you need to watch out for order stats, right? I mean, what I'm saying is you do notice, I hope you appreciate the difference between this problem where no derivative is going on with the problem of, let's say, the you know, the normal, where you just differentiate, you know, make things, you know, smooth, and the exponential, right? I'm sure as a student you would prefer this, right? Or even this, and you would not prefer the uniform. But you know, life doesn't give you a choice. You just have to deal with anything that comes your way. So the answer is, right, this approach shows up when the support of the population distribution depends on the unknown parameter. Okay. So pay attention, right? When we say, for example, I hope you know what I mean by support, right? Support is where the density is non-zero or where the probability is non-zero. Okay. So there are two places, right? When we say, for example, we have a density, right, that depends on theta. We never say, for example, how theta comes into the density. Theta can come into density in several ways. It can come in like this, right? So the theta affects the value of the density, but it does not affect the support, right? You see here, right? Support does not depend on theta. Yes, because support is from 0 to infinity. The support can depend on theta explicitly, like, you know, let's like this, right? Here, let's say this is a uniform, right? This is uniform from 0 to a. This is uniform from 0 to a, right? So here, actually, you see the parameter affects both the density and the support, right? So here, support depends on. Okay. And when support depends on the unknown parameter, you can bet that somehow all the statistics will show up. If it doesn't, I'll be super surprised. Why? Because, right, in this way, you see somehow the maximum will tell you something about A, right? The maximum will tell you something about A, the sample max. So if the sample max doesn't show up, oh, okay, I'll take it back, right? If you use the moment method, all right, if you use the method of moment, then no, all the statistic doesn't show up, because that's a different philosophy. You just take the moments, right? But if you take the maximum likelihood approach, then of course you need to care about where, right, where the density takes value. So therefore, right, the order the maximum will show up. Is that okay? So pay is a habit of a student, okay, from probability not to pay attention to the support. I know that, okay, because I've seen many. But in the case of doing statistics here, right, if you don't pay attention to your support, it will cost you, okay? It will cost you. Depends on the problem, right? This problem, it doesn't. I would say if you forget that the support is this, you're fine, because there's no data show up here. So whatever you do is implicitly correct. If you were to do something like this here, right, like I demonstrated, you will, right, pay for it. It can be a mix too, right? It may not come in the obvious case like this, because now you see this, you notice, you watch out for the uniform. But no, right? Things don't have to be that way. I think that in your textbook, it may be something like this. I may forget already, but it could be this. Could be C, like like this, where theta less than x less than 30. Okay, so let's say here theta. So here, of course, C depends on theta, but the textbook asks you to decide what C is. All right. So this is another case of a distribution whose support depends on theta. Okay. So if you were to do maximum likelihood for this family, you will need to use the order statistics. You will need to watch out for differentiating with respect to theta does not make sense. Z equal to 0 does not make sense because of this. Okay. So here, support depends on theta. Okay. So in the case where the support depends on the unknown parameter, differentiating with respect to that unknown parameter, right? So if support, right, depends on theta, differentiating and set equal to 0 may not make sense. Should not make sense. Okay. The reason is because the indicator function, right, will say that it's not differentiable there. So when you look for the derivative equal to 0, you're looking for the wrong place. Is that okay? Any question? Okay. So now I think we have introduced two methods, right? So we introduced two methods to find estimators. So to recap, right? 10.7 and 10.8 introduce you to two methods, right? Method of moments and method of MLE, right? They are, so, okay. So are they different or the same? I hope that you see that they're different, right? They're different methods, right? Sometimes they agree, right? Sometimes they agree. For example, right, you see the exponential, right? X and exponential lambda. Then lambda hat of moments equals to lambda hat MLE equals to X bar. We say that, okay? But, sometimes they disagree too, right? And by disagree here, I don't mean anything bad. They don't argue. It's just they give different answers, right? For example, if you have the uniform, right? Then the A hat, right, MLE is the minimum. The B hat, MLE is the max. And on the other hand, does anyone remember what the A hat moment is and the B hat moment is? Do you remember what they are? So they are like confidence interval, right? You start from the sample middle, average, right? Add and subtract, if I recall correctly, I think square root of 3 S prime. I'm not positive on my square root of 3. I think it's square root of 3. I hope I'm right. Okay, appreciate it. Yeah, right. I'm very sure about the structure. I just forgot what the constant is. But anyway, right? You see, they are different. Yes. And when they're different, then they're obviously the question of which one's better. Okay. So, I mean, I guess being human, right? We want to go for the best, whatever that means. So, how to compare them? Okay. And how to compare estimators or how to judge, right? The performance of estimators in general is a big topic, right? Or actually is one of the topic of statistics, right? You can see that statistics maybe fall into two areas. I mean, to oversimplify. One is how to find estimators, okay? And that is just not in this kind of thing, right? There is much more sophisticated than that, but roughly how to find certain estimators. And B, how to judge its performance. Okay, but of course, how to judge its performance is, to begin with, you must have criterion, right? Criteria, and many criteria have been invented, right, to judge. But one of the most traditional one, I guess, as old as time, is one of the traditional one, right? Is the MSE. Okay, MSE stands for mean square error. All right, you will hear the word MSE a lot, especially in regression and that kind of thing. Those of you who are into, I don't know, machine learning and all those, fancy new things, MSE will show up a lot too. Pay attention, right? It's MSE and not MLE, right? MSE, MLE, MSG. MSG is not statistic, right? So anyway, so what is MSE, right? Mean square error is what it is, right? MSE, when you estimate a parameter, right? MSE of a parameter will be just expectation of theta hat minus theta square, right? So if you have theta hat, right, for theta, then MSE of theta hat, right, is going to be that. What does it mean? It's actually very intuitive, right? This, again, emphasizes the nature of theta hat as a random variable, right? Every time you do a sample, you get a different theta hat. So on average, right, what is the error you're committing? Now, of course, when you do this, you do not care for the sign of the error, right? Because if you overestimate, it's as bad as underestimate, I guess, right? So you square it to get rid of that sign, okay? At least that's one of the implication. And then you take the average, right, over all possible samples you could have done, and that's going to be the MSE. Okay, so very easy way to define. Of course, unraveling this guy is just a different story. But right, what can we look at in terms of the MSE? So the MSE, right, being the expectation of the square, right? This is where probability comes in. Probability is very, kind of pedantic. It says, yeah, that's the second moment, right? Shouldn't it be variance plus expectation of the square? Hold on. Yeah, I think that's right. Right. Is it okay? You see what I'm doing here, right? The expectation, right? This is like expectation of x squared is variance of x plus expectation of x squared. Yes, that's all I'm doing. Where of course x here is theta hat minus theta, which is the error. Okay. So, right, you see then from probability point of view, you have two components that comes in to make up the MSE. One is called the variance, of course, but the textbook will call it efficiency. Okay. The second one is the square of a quantity is called bias square. All right. Bias because it's just basically, on average, how much error you're making, right? On average, how much error. This is, I guess, right? So you see the MSE, by the way, is the error square, right? Average. The bias is expectation of the error and then square. I mean, if you want to square the bias, right? But anyway, right, the mantra, as you will see, right, I hope this is not the first time you see it, is mean square error is variance plus bias square, right? So these two together will allow us, right, to judge performance of parameters, or the traditional measure, right? You want to see how the efficiency gets compared, or how the variance gets compared among different parameters, how the bias gets compared among the parameters. And then if you want to, right, you can combine them in this way and get to the mean square error and compare them. Okay. All right. So that brings us back to 10.2 and 10.3, where not surprisingly, 10.2 study bias and 10.3 studies efficiency, or exactly the variance. Okay. So that's all we'll do next. Any question? All right. So, right. So again, remember, right, the theme is very clear. We have discussed how to find estimators, right, among many other ways. I don't know, right, among ways that you can just think of yourself. Now, in the case where we disagree, meaning in the case where we come up with different estimators, how do we judge the performance? I claim, and actually this is tradition, right? MSE is one of the most reasonable way to do it. And MSE gets broken down to bias and efficiency. So we study this. All right. So bias, right? So I guess, I don't know. If you want the bias, there's nothing officially defined as bias because of the sign. I don't know if it's theta hat minus theta or theta minus theta hat, but the traditional definition of bias goes with the unbiasedness, right? It says that, so 10.2, right? Theta hat is unbiased for theta if expectation of theta hat is equal to theta. Okay. But of course, you see that in terms of the thing I'm writing here, right? That just means that the bias here that I'm talking about is zero, right? So theta hat is unbiased for theta if the bias is zero. But of course, when it's biased, then there's no, as far as I know, I'm not sure which the exact sign, right? Is it one way or the other? But who cares? So if it's unbiased, then that's good. So otherwise, it's biased, right? So it's as straightforward as it can get. For example, right? X bar is always unbiased for mu. This is one of the thing that we established right from week 2, because expectation of x bar, as we always say, is mu. That's it, right? S square is always unbiased, right, for sigma square. Why? We established that too. Expectation of S square is always equal to sigma square, right? Universal. As long as we have IID sample, we have this. Okay. So along that, right? So you have things like S prime square. Remember this guy? This guy is the one that will show up in estimators in general, right? S prime is xi minus x bar square over n, right? So in some sense, S square is the one we use, but its cousin, right, is the one that naturally show up in the method, right? Naturally show up. Why does it naturally show up? Because we have sample size equal to n. So when you maximize or when you take the moments, it just naturally divide by n. You don't have n minus 1 to divide from. But anyway, right, the point, now you see the point, right, is this guy naturally shows up, but is biased, right, for sigma square. Why? Because when you take expectation of this guy, right, I mean, what is it? Is S prime related to S square, right, by the fact that it's going to be n minus 1, right, S square over n, like this. We know S square is unbiased for sigma square, so we got that to be sigma square, like that, right? So not only that we know S prime is biased for sigma square, is always, right, always underestimate sigma square, right? Not that you always know that, but here, right, is always underestimating sigma square. And of course, you see that the smaller the sample, right, say n equals to 2, right, then that's pretty bad, right, because it's estimated only with a half. All right. Any question? So, the textbook mentioned this kind of weird example. I don't know how good that is. I think it's kind of pretty obvious, but I just want to mention anyway. So the definition of biasness requires that expectation of theta hat is equal to theta for all theta. Okay, for all value of theta. And they give a weird example like this. I don't know how, again. So let's say example, let's say you have x1 up to xn, let's say IID exponential 1. Okay, exponential 1. All right. And let's say you come up with some lambda hat. That expectation of lambda hat is equal to 1. Okay. But in general, right? But in general, expectation of lambda hat is not equal to lambda. You understand what I'm trying to say? I mean, the textbook has some example. I don't care to kind of reiterate because I think it's not too enlightening. But the point being is just in the particular case when lambda equals to 1, then whatever the estimator is, it happens to be equal. But in general, it's not equal to lambda. So in this case, even if the true lambda equals to 1, you don't get to call this unbiased. Okay, that's the message. That suppose that it's a lucky guess. Like suppose that somehow you hit the true target for that particular case where the true target is 1, you don't get to call yourself unbiased because you're not unbiased in general in terms of the lambda. Okay, so that's what the book says. It's a very weird point that I don't think it happens in real life that much anyway. So I don't want to say too much about it, but here, so lambda hat is not unbiased. Okay. All right. I just realized that time is up. So I think it's a good place to stop here. We'll continue with unbiasedness and stuff next time. All right. If you have any questions, I'll answer. If not, see you on Friday. Thank you.
I have a question.
Mm-hmm.
So actually, it's not about this class. It's like I just realized that there is something wrong with quiz 2 solutions for the first question.
Okay, what is wrong?
So
Friday, the last
you
day.
said, yeah, maybe it's better for you to take a look at it. So you said u is equal to x times 1 minus 2t.
Yeah, 1 second. One second. Let me
Yeah,
ask Alice.
it's better for you to open it up.
Sure, sure. Yeah, Alice, the Friday will be a last day for the recap of new material. Yeah. All right, so let me take a look here. Let me stop recording.